Service system efficiency hinges on understanding how requests move through processing stages. Picture a system with multiple service points, where items progress from waiting to active processing. In this framework, two critical concepts emerge: inventory in service and inventory waiting, or inventory in queue. Inventory in service represents items currently under service, while inventory in queue captures those pending processing. These perspectives provide insights into system dynamics and resource utilization. Flow time becomes a pivotal measurement, encompassing the entire journey of an item through the system. This comprehensive metric integrates two fundamental components. 1. Service time, the duration spent actively processing an item. 2. Waiting time, the period an item remains in the queue before receiving attention. In this formulation, the number of servers, M, is introduced. More servers generally lead to shorter waiting times. This is because they can service requests simultaneously. The waiting line model helps us understand service systems. It shows how customers enter, wait, receive service and then leave. At the start, customers enter the system. This is called inflow, represented by a flow unit entering the queue. The flow unit moves to the first service area. Once in the system, customers may have to wait. They can wait in inventory, which is the group of people before them. This waiting inventory is labeled as IQ. After waiting, customers move to the server, the resource that provides the service. The server helps each customer one at a time. When the process is complete, customers depart from the system. This outflow is shown as leaving the server and moving on. In the waiting line model, timing is crucial for understanding how flow units move through the system. Here are the main timings involved. 1. Waiting time. T1. This is the time a flow unit waits in the queue before it can start being served. The longer the wait, the more frustrated customers can become. 2. Processing time. P. Once a flow unit reaches the server, it begins processing. This is the time taken to complete the service. Efficient processing minimizes overall delays. 3. Total flow time. T. This is the sum of both waiting and processing times. It captures the total time a flow unit spends in the system, from entry to departure. Another key concept is flow rate, which refers to how quickly items move through a system per unit time. This rate is calculated by comparing the flow rate to the system's capacity. It's important to ensure that the flow rate is less than the capacity, as this condition allows the waiting time formula to function correctly. In inventory management, we focus on specific formulas to help us understand and manage stock levels. Inventory in queue. IQ refers to the inventory that is waiting to be processed or in queue. Inventory in process. IP indicates the inventory that is currently being worked on or processed. The resulting inventory, I, is the total inventory in the system. Note that this is Little's law in action. In a stable system, several factors determine how long something waits in line or queue. Let's break this down into simpler parts. The capacity factor tells us about the system's average processing time. Here, M represents the number of servers. The capacity of the system doesn't change with demand. The utilization factor connects demand with the system's performance. This shows how demand affects the queue length. The average demand influences how resources are used. The variability factor indicates how much demand can change. More variability means longer wait times. If demand increases suddenly, queues may get longer because the system is not ready for such changes. All these factors work together to explain why and how long items wait in a stable system. On the left, we have the stable queue. In this system, the utilization is 86%. This means that the servers are busy but can handle the flow of customers. The total number of customers stays relatively consistent. On the right, the unstable queue is shown. Here, the utilization jumps to 114%. This indicates that the servers cannot handle the incoming customers effectively. As a result, the total number of customers in the system keeps increasing over time. The table shows the historical into-arrival times in minutes. It helps us understand how often events occur over a specific period. Observe that the mean is 3.32 minutes. The standard deviation 3.31 minutes. The coefficient of variation, CV, is calculated by dividing the standard deviation by the mean. This value helps us understand the relative variability of the into-arrival times. In this example, the PV is 1. Consider arrivals at a post office between 2 p.m. and 6 p.m. Observe the increased frequency at 0 to 2 minutes in a histogram. It means many customers arrive close together. In the case of random arrivals, CVA is approximately 1. On the left side of the slide, we see scheduled arrivals represented with a histogram. The x-axis shows into-arrival times in minutes, while the y-axis indicates frequency. Here, the into-arrival times range from 0 to about 16 minutes. Most of the arrivals cluster at shorter time intervals. This suggests that the arrivals are fairly consistent and predictable. Now, let's look at the right side of the slide, which shows grouped arrivals. The histogram here also measures into-arrival times. However, the distribution looks quite different. The values extend more widely, showing greater variability in how long it takes for these arrivals to occur. Understanding these differences helps us analyze how arrivals are managed and scheduled in various systems, such as airports or customer service centers. It's essential to recognize how variability impacts efficiency and planning. Stay curious and keep exploring statistics. The coefficient of variation, CVP, helps us understand the variability in processing times. It is calculated as the standard deviation of processing times divided by the mean processing time. Let's break this down further. There are 3 key concepts. 1. Processing time. This is how long it takes to complete a task. 2. Standard deviation. This measures how spread out the processing times are. A low standard deviation means that most processing times are close to the average. A high standard deviation indicates more variability. 3. Mean processing time. This is the average time taken to process tasks. The graph shows processing times that are relatively normal. The coefficient of variation, CVP, is close to 1. This means the times are fairly standard, and tasks are processed predictably. The bottom left graph features more consistent processing times. Here, CVP is less than 1. This indicates that the variability is low, and most tasks take a similar amount of time. The bottom right graph reveals a high variability in processing times. In this case, CVP is greater than 1. This suggests that there is a wide range of times taken to complete tasks. If you enjoyed this content, please consider liking and subscribing. Thank you.